I'm going to try. I mean, I haven't figured out yet. Oh, it was working a moment ago. Oh, now. Um, so again, we're going to try again. It doesn't work. I don't know why. It doesn't show the results live. But I'll try something different now and see if I can make it work. You saved the address, right? So I don't. Okay. Come on, you work a moment ago. Oh, now. Okay, good. No, okay, it's not working. We'll skip it.
यहाँ पे आ रहा है. It's coming on our screen.
Oh, the question is coming in your screen? Okay. Yeah, so the next, so if you go to polev at that address, FLOPZ048, I can put it back on. Let me see. Oh, I need to point there, right? I don't know why I'm pointing to the screen. You know what? I'll just sit. So if you go to this address, you remember it? Okay. So I think you're going to get a question, something like, what bioinformatics tools are you aware of? So if you don't mind typing what tools you are aware of. Any. Pick one. And if you, so the trick though, if it's a multiple word, don't use white spaces. Use an underscore to connect the words.
We have heard only the name. We are not actually aware of it.
You know any tool? Just write down the tool, the name of the tool. Anything that comes to your mind. What tools you are aware of? Yeah, so if you're going to type bow tie separately, you need to use the underscore. So I can see somebody mention Trimomatic, FastQC, Picard Tools, Anovar, SAM Tools, some databases like CleanBar, HiSat2. So everything quite focused on alignment, annotation, R, BLAST, okay, Python. Okay, I don't know if it's going to be readable. Yeah, more or less to give an idea, right? So so yeah, you give a lot of good ideas, right? All these are programs that we use for analysis, even databases, some tools for visualization like IGV. I can see annotation tools here. So we need to define bioinformatics, right? The first thing I did, I went to the Wikipedia. Sorry, I'm in the middle again, right? I went to the Wikipedia, and one of the things that the first shocked me, right? So it mentions that it's an interdisciplinary science, which is true, right? I mean, maybe not in the tools that we were talking about. All of them were about genomics and annotation, a lot of alignment tools and things like that. But yeah, definitely bioinformatics includes, programming, math, statistics. Somebody was mentioning R, definitely. Nobody mentioned anything related, I think, about protein structures, but there's bioinformatics in a lot of different fields. It was there? Okay.
No, I don't think it was there.
Oh, okay. Yeah. AlphaFold, all those tools, right? Creation of algorithms. So math is there's a lot of involvement of math too.
But have you come across
Which one? Sorry. Oh, the one from Google. Yeah, I don't
No,
know.
no. For like FMF,
Okay.
familial medical fever. So some of the MEFE variant it was calling benign, which were clearly pathogenic. And alpha missense was calling them benign.
Yep. So yeah, quite interdisciplinary, right? I think all of us could agree on this. Um, so that has an implication, definitely, which is the skills required to be a bioinformatician. If you need to match all the fields, it's going to be complicated. But definitely, there's a long list. And here, probably, I'm just listing whatever it come to my mind at that moment, right? So programming. As you can imagine, you're going to need it at some point. Sooner or later, you're going to need to learn some programming skills. Definitely, you need the statistical thinking, data management, biological interpretation, and things that you probably don't think that much, but data ethics and privacy, it's also involved, right? When you work with bioinformatics, especially if you work in a clinical setting. And nowadays, it's very difficult not to talk about machine learning when you work in bioinformatics. So another thing you probably noticed, right? So when we talk about bioinformatics, we talk big files, a lot of sequences, and things like that. And generally, a laptop, it may not be enough to do what we do. What we generally do is generally use the laptop as a Windows to connect to a bigger server, right? Working in a cloud environment, or in this case, this is a picture of I think this is the old one actually. This is a very old picture, but the cluster that we use at the Genome Center. Was the old cluster that we use at the Genome Center. But it also exists other type of clusters that you connect to.
In your center, how much of data is stored in your servers? Like petabytes or like?
So I don't know how much we have stored. I can tell you we store everything since 2009. But
A lot of data.
yes, a lot of data. The funny thing is I remember like the first year we used to tell to the user, oh, we're going to erase the data in 1 year. So it's better you figure out a way to store it and something like that. That wasn't true until 2016, after a few years. And then we start remove them from the actual cluster, but we have a backup. We used to have a backup tape. So the old classical magnetic tape, because it was really cheap, we stored the data on a tape system. Nowadays, I'm not sure, but I remember, I don't know if Bonnie knows. Bonnie knows more the economics of the center.
Is it economical to say RAM or CRAM, or what is economical to say?
We store the raw files. We didn't store FASTQ files. We never store anything processed.
Are they bigger?
Yeah, they're probably bigger. We could use CRAM and store the CRAM and then transform it back to FASTQ if you need to.
Yeah.
But no, we from the beginning we start storing FASTQ and that's where we stay.
One thing actually you should think about when you are thinking, one of the biggest challenge for genomics at this point is data storage. Okay, because we are creating data at a speed that we don't have that much ability to store. So archiving, and between this CRAM formats or any other compression formats, the biggest challenge is the downstream pipeline needs to be accommodated, like CRAM files. They're actually Lumina format. That means you need to actually have some way of decompressing it, and that means you need to pay something for that, those kind of things. So when you're storing that in a certain format, you also should think about is your downstream pipelines are compatible with your compression, and what it will cost you to decompress it. So compression in CRAM compression from Illumina is free.
I'm blocking.
Decompression you have to pay money.
I'm good, or I'm blocking?
So that is clouds and everything is paid, but then those are the things that you should really thinking about,
Like moving like this.
how often you are going to download the data, because most of the cloud will have very limited amount of money for very limited cost for uploading. The cost is in download, so you are frequently downloading, then you are going to spend a lot of money.
If we want to store the human genome data, and how much we can store it?
So
The bigger
usually
computers.
what we do, we store data only for 6 months, and then we archive it in the tape.
Yeah.
So we
Well,
move it to the tape archival system.
I think the tape is gone. I think we will use now a different system. But I remember the cost, I remember at some point the cost only of all data saved, it was $10,000 per month.
Yeah.
And then we realized,
So isn't it good enough that if you want to sequence it, resequence it rather than store it? So there's now a lot of talk that rather than storing, which is so costlier, you might as well resequence it.
Store the DNA and
But the problem again, see, if you are working with a research sample, you will have enough sample to do that. But most of the
If the
data
individual
samples
is there,
probably
you will
don't have that
But
much.
it might change if we are looking for some
Yeah.
health.
If it is temporal, like it has changed over
Yes.
time, then probably.
we still go back to data in 2012.
Yeah.
So
Storing is still.
so we need to store it because people is asking for data from as old as 2012.
And there was some talk about, I don't know how far it has gone, that the best way to store data is like how it is stored in the DNA itself.
Okay, so I should tell you
I
one
mean,
story.
like, so there was some project
I work with it.
where they're trying to store
The picture of
data from the genome in the format of a genome itself.
Yeah.
So I will tell you one story. You have that picture of you holding that capsule. You had to take image.
oh, I don't know what that picture
So
is.
this is an interesting thing Praveen mentioned. So Francis was actually involved in a project where two novels, books were stored in a capsule in a DNA format. So what they were doing, they were actually taking. So this is the lifelike DNA. You add water, you make library sequencing, and then stitch it back, and it will give you a novel protein.
Well, there's a conversion system, right? So the DNA would give you back
And so
the
Francis
book.
was analyzing that, like he was creating that book back, I remember. And he had a picture, I still remember, holding that capsule in his hand.
How big were those novels?
Oh, you can store a lot of it.
War and Peace of Leo Tolstoy?
No, I don't remember what books were. I completely
Yeah,
forgot.
we did it back in 2022, and this was the first time Swiss biosciences were doing it. And now this idea is new because of they had a way of making. So one of the costliest things, cost issue in this approach, like when you say something in DNA format, is the cost of oligosynthesis. So Chris came with an idea for that instead of sequencing, making individual oligos, they do something called pooled oligosynthesis. That is, they create a pool of oligo on a slide. So that reduces the cost. And so that is why they were testing the storage one. And they reached out to Francis for that, and then we did the sequencing and Francis did the analysis.
So you will be presenting something related to
No, no. It's Bonnie.
You mentioned so we just go to.
Yeah, you mentioned, so now that I remember, we don't store the FASTQ as a GC, we store them as a cube, which is a little bit more compressed. But also, you have the problem that those systems, they are not supported anymore, right? So the algorithm is not supported anymore, so we have to change to something different now. So I don't know what we're going to do next. Well, so coming back to the tools we're using, right? So the idea was we're doing an overview of the tools that you need or what kind of skills you need to learn, right? So one of them is probably sooner or later, maybe that your project is small enough that you can use a laptop, but it's quite often that we need to use more power, right? And for that, it's what we use is high performance computing, HPCs, or whatever you want to call them, or even cloud systems like AWS, Google Cloud, etc. So now I have a question for you. So if we need to divide in a big different, so I generally think about how we communicate with computers in two different ways. So can you tell me one? Commands, right? The graphical interfaces, right? Yep. So that's the two main ways, right? So you can use a graphical user interface with point and click, and the computer responds with something. Or command line interfaces, right? So when we think about tools, you can think in the same way that you could divide them in two big groups, the graphical user interfaces and the command lines. And each one of them has advantages, right? I put some examples here on top. For graphical interfaces, I don't know if you heard about Galaxy, but you have other commercial ones, right? Or command lines. You mentioned, a lot of tools that you mentioned when we asked the questions are the command line ones. I don't think anybody mentioned any commercial ones, right? Or graphical user interfaces. Each one has their advantages. One of them is they're easy to use graphical ones, right? You point and click and you get something. They are not that flexible. That's a problem, right? It's complex to create flexibility on a graphical user interface. So with the command lines, you can create pipelines, so they're really flexible. Generally, graphical interfaces are going to be slower. These ones are generally easy to use in the high-performance computing systems. As I said, most of them are commercial, so you're going to have to pay. And that's the main issue. Galaxy being the exception. And if I came up with the idea of what they're good for, right? So if you need to do quick analysis, maybe these type of tools are the best. Or if you have a small batch of samples, a graphical user interface can be good. If you have a lot of samples, you're going to probably, sooner or later again, move into high-performance computing and using command lines. There are exceptions to everything that I'm saying, right? So these are general ideas. I especially like Partec Flow. I don't know if you've heard about it. It's a graphical interface that allows you to build workflows, and they are quite flexible. You can put pieces of a big puzzle and then create parameters whatever you want. So at the end of the day, it's pretty similar to what you do in a command line, but in a graphical interface. The main issue is you think, okay, they're easy to use. Well, to some extent, yes, but you need to know what you're doing, right? So in the same way, you need to know what parameters BWA uses, right? In the same way, when you build this type of pipelines and you want to be flexible, you need to be aware of all those parameters and what each one of them do. So Galaxy is another one that I want to mention because we are not going to use it in this as a graphical interface. Can you raise your hand if you heard about Galaxy before or use Galaxy? Oh, not many. Okay. So Galaxy, I think, is a really cool project. So the idea is to build workflows or tools. They have, I think they mentioned they have over 10,000 tools available in their website. So you can do a lot of different things related to NGS analysis. You can build your own pipelines, or you can use whatever other people has built before, right? So you can run analysis in there. Of course, the main issue is currently there are only, as far as I know, 3 public servers or 3 public web servers. They have Galaxy. So I think it's US, Europe has one, Australia has another one. It's slow. That's the main issue, right? They're far away. They're generally slow. If you need to upload big number of samples, it's going to take forever. So again, it's the limitation of the graphical interfaces. But if you have a small project, you have one sample, you could start learning to do bioinformatics just using Galaxy. They have tutorials too. So you can go there and say, okay, I want to do variant calling of one sample, and they will teach you using a tutorial how to do it. We're going to do a little bit of Galaxy, just a little bit. Another tool I want to mention is the UCSC Genome Browser. It's a tool, and at the same time it's a database, right? How many people have used or heard about the browser? A little bit more, okay. Yeah, but it's still not everybody. So this is the view of the web browser, or one view that you can have. I mean, it can get even more crowded than this. So it doesn't sound like appealing, but the coolest thing is you can visualize the whole genome there. You can have a lot of information in a website, just in the top of your browser. And it's amazing how responsive it is for how much information you can put on the screen. So yeah, we're going to use it. So let's do one thing. Let's try to do this exercise. So we can go to the website of the genome browser. It's called genomeucsc.edu. I'll keep this instruction on the screen. If you can follow them, or if you cannot follow, let me know, and I'll do it myself. But the main idea is we're going to select. So one of the first things you're going to see is in the top left corner, I think it is, you have like a menu, and it says genomes, and a drop down, and you can select the human genome, and you can choose the HG38, for example. And if you want me to do it, I can do it live too.
You could click on the link and do it live.
Yeah. So let's see what I mentioned. We're just going to play a little bit with that. First with BRCA1 gene, and then FOXP2 EX47. Okay. So this is the look. Right, I'm going to zoom in a little bit. So if you go to genomes, sorry, I shouldn't have clicked. Come on. Here we go. I said it was responsive, and it doesn't look like it's that responsive anymore. Were you able to follow, more or less? Yes? Okay. Yeah, you're going to get a view like this, right? So here we have chromosome 11. I don't know, you may have something different in your view. I don't know if this was maybe the last thing that I did here. You have a search bar here that you can search for anything, pretty much, of you can think that is being annotated in the human genome, like a gene or a region or things like that, or even other annotations like you can search for ClinVar or dbSNPs or things like that. So if I type, so actually I have my search here. So BRCA1 is going to show me, it's going to go straight to okay, BRCA1 now. So all these things that you have here, they're called tracks, or you're divided in tracks, right? And it's information about the human genome. So generally, the first one you're going to see, and I think that is always there, maybe you can switch it off, I'm not even sure, is the annotation of the region that you're looking at, right? So here we have BRCA1 gene, and this line here is how long is the gene, and the thick lines are the exons. Everything that is thin in the middle is going to be the introns of that gene, and you can hover it of one of the region. It would tell you, okay, you're looking at exon 10 out of 23. It gives you some information about that, right? And it gives you what transcript are you looking at, because each of those lines are different transcript or isoforms that have been annotated for the genome. I think in the HSIs I mentioned that actually have it. If you go, sorry, this probably is not on your view, but if you go at the very bottom here, you have all the tracks available. So all this is, if you switch it on and off, you can see it on top of the track. So for example, I mentioned if you go to clean bar, which is this one here, that is now activated, you're probably going to see this if you go to the clean bar section. It says hide, and you can put it, let's do dense, for example. This is the way it's going to show that track on top. So dense means is compressed. If you do full, it's going to be very extent of information. I'm going to do dense, I'm going to refresh. So if I go back up, sorry, all this is clean bar already, but it's full, sorry. You're going to get a new track. Okay, here we go. It's reloading. We still have BRCA1. And here we have clean bar annotations. Clean bar is a database for variants associated with clinical outcomes. So it can be pathogenic. There's also, so clean bar is a bit complicated in the sense there still can be, they're classified based on the pathogenicity, right? They classify as being pathogenic, likely pathogenic, benign, or unknown, what they call unknown significance. We don't know exactly if it's pathogenic or not. There's a lot of type of variants, not only clinical related. There's also levels of classification. They give them stars depending on if multiple people have seen that variance being associated with disease. So it's going to have multiple stars telling you, that, oh, I'm confident that this is a real variant. There's still a lot of false positive, and it's a big effort nowadays to clean up the system. So they're removing those false positives or changing the classification. So of course, BRCA1 is a gene related to cancer is going to have a lot of clinical variants annotated. And if you want to extend it or look at one specific one, you probably can click on one of them, just randomly. It's going to extend it. Yeah. Again, I said it was responsive, but it's not that responsive anymore.
What is this color indicating? Or the
Oh, I'm not even sure what the clean bar says here, but yeah, it must be if it's pathogenic or benign or things like that. You're probably going to have to check. Pathogenic, right? So red means pathogenic, blue probably means something different, right? Oh, they're all pathogenic? Oh, yeah. So these big lines probably means it's an indel.
It tells about the type of variant and the pathogenicity of the variant.
Oh, you see the star system? So if you scroll over one of them, you can see here on top, they give you 1 star, right? So it means it was a single person that submitted this indel that is expanding from that position to that position. So you don't have much confidence that being real if only one person have reported this to CleanBar, right? But if you have more stars, you can be more confident that that variant probably is real. So if you want to try something different, I mentioned to look at this other gene. It's called FOXP2. So it's already searching, yeah.
So this software will tell you the clinically defined variants, right?
Yeah, so the ones that somebody reported to
We
me.
get the information from this. So if we want to check some genes like BRCA1,
Yep.
BRCA2, we will first look into the clinical variant, what this software is giving us.
Okay, so this software, the only thing it does is to show you data. And it can come from a lot of different databases. The only one, what I was trying to do is to show you one track, which is the CleanBar one, but you have a lot of different tracks there, and I'm going to show you a different one now. The CleanBar database is basically a database that is not this, it's separate. So this, what it's doing is taking the data from that database and showing it to you. The ClinVar database is just that, a database of clinical variances related to some clinical outcome, right? So yeah, now we have a new gene, which is the FOXP2. In the same way, it's very long, or it seems long, or there's a lot of big, long introns in it. And these vertical lines, you don't see them, but they are exons of that gene. So I still have, these are the clinical variants again. Probably, I still have it active. As you can see, there are less. Oh, here we have them classified by the interpretation: pathogenic, likely pathogenic, variants of unknown significance, likely benign, and other. So these are the type of classification. But you can see that this is less crowded than BRCA1, right? And we have less indels reported here. These are just single base annotations. So these are the IDs for DBSNP. I don't know if you're aware. This is a different database on just people report SNPs. So let me go down. I'm going to try something different this time. I'm going to switch off ClinVar, so I don't want to see ClinVar. And let me go. It's still refreshing. So if you are done refreshing, you can try this multiple alignment. Okay, now it's refreshing. So before I activate multiple alignment, another thing that you can show, if you want, you can drag the track, so you can move it left and right, and it's going to move. It's going to refresh and only refresh that window. So you can, navigate the genome really easily on this website. The other thing you can do also, if it stopped refreshing, let me reload. So this is exon probably 3, exon 4.
The transcripts in the UCSC, are they mentioned in ENSOM transcripts? ENSOM.
The ensemble, yeah.
Why is that? Because it is from the US and not from the European consortium. So why do they choose to?
Yeah, I don't know. Maybe you can have both. You can have your own custom track. So if you go to another database, you can get a bed file and upload it here.
On UCSF, if you want the equivalent, like NM for the same ENST or the ENSOM transcript, can you do that?
Probably you can do that. Yeah, I mean, you have NMs here on the bottom, I can see in this section. This is the annotation of UCSC, but I'm assuming you have all other type of annotations. I don't play enough with UCSC Genome Browser to know everything what is here, but I mean, you can see there's a lot of tracks to use. So one other thing you can do is, for example, I think this is chromosome intron. This must be exon 7. So I'm going to try to zoom in. Sorry, I'll just move it again. Oh, by the way, here on top, you have that red line is the area where zooming. And of course, you have the zoom in and zoom out option, so you can have a bigger visualizations. Let's see if I can. We said that was exon 7, right? Yeah, that must be it. So I'm going to try to zoom in. What is the exon 7? Is this one? No, don't do it. Let me do it better. Ah. So you see, I just drag and drop, selected an area, and in theory, I'm going to be zooming to exon 7 now. Is this exon 7? Exon 8. Okay. Let me zoom out. Let's see if I can do it manually. it's going to take too much effort. I'm going to quit. Okay, exon 7, I found it. So this is exon 7. I'm going to zoom into exon 7. And if you keep zooming in, you're going to see the sequence itself, the DNA sequence. We actually see now the protein sequence. Right? In the human, you have the different isoforms or annotations in different databases. So if we go down, and for example, I said, I don't know what I did now. I hope I didn't move it. I went back, right? Yeah. Okay, exon 7 again. So by the way, there are multiple genomes. There's not only the human genome. You can have other genomes. So if I select this, oh, I already have it. Let's do dance. So what track is that one? Oh, here we go. So you can have even your sequence being aligned to other species if you want to, right? And I picked that gene. I was trying to find genes that are interested. I picked this one because this is related to language. And if you can see, pretty much it's a well-conserved gene across multiple species, right? Except there's only a couple of places that unique to humans only. So there's only one amino acid change that seems to be completely different to the rest of the species. And there's theories about that amino acid change being important for us to be able to speak compared with other species, right? I don't know, I just wanted to show up a little bit the capabilities of UC Genome Browser. It could be a really cool tool for you if you want to explore the genome in a website. Although it looks like an old-fashioned website, you can have a lot of information in a single tap in the browser. So coming back to so another cool thing is that, well, I explained all this. I mean, we don't have to do it. I mean, we already spent enough time. But if you want to, you can look for this SNP. This is the SNP definition or ID in the DB-SNP database for one specific SNP seen in humans. And it will show up in the track as being pathogenic, right? We don't have to do this exercise. We're going to skip it. But this type of job you can do. If you have a DB-SNP annotation, you want to know if it's significant for something, you can go here and search for it, and you have all type of annotation, what it is in the genome, if it's conserved across different species, if it's clean bar or not, interesting, things like that. Another cool thing about the genome browser is it's connected to Galaxy. So if you want, we can do this exercise, or you can try to do it. Let's see if it works. You want to do it? So if you go to again, to UCC Genome Browser, oh, this is not the exercise, my bad. So I'll show you in a second. But basically the idea is you can connect, whatever you're doing in the genome browser, you can connect it to Galaxy. You can send it to Galaxy for more analysis. So we can do this exercise. So let's imagine we want to get all the coding bases of BRCA1. We want to remove all the introns. We only want the coding bases. So what we can do is we can go to the genome browser. If you go to Tools, Table Browser, and you do this, you're going to end up with what we call a bed file, which is going to be defining all the exons for that gene. So please try it. I'm not going to do anything else. You have the instructions. I think you should be able to follow them.
Just do it and let us know that we take it. And we have two wonderful volunteers, three wonderful volunteers. This is the third wonderful volunteer. Okay, so
Or I can go back and forth and show you at the same time and keep the instructions.
if you need any support.
So we have other people.
Yeah, so if you other people are there, but then of course, any help you need, please.
और you can sit there and अपने आसपास के लोगों को साथ हो गया
Once you're done working, guys, just help us.
अपने रूम के आसपास
People help चाहिए, you can.
So this exercise is only to show you how you can connect two different, or in theory, two complete different websites and use the tools of one with another, right? Any problem finding the table browser? So you have two ways in the UCSC genome browser. You have two ways to look at the genome, right? One is the one that I already showed you, which is navigating through the visual part of it. But you can actually use a table system. They call it a table browser, where you just say, oh, I want all the information related to BRCA1. You type the name, and you're going to get some tables about it. Can I help here, maybe?
So table browser.
Yep.
So yeah, we have to
Yep.
select
So,
entity and
yeah. So basically, I'm going to tell what you're doing in every step here if you want to. So basically, we're asking, oh, can you give me the gene predictions, the annotation for that gene, right? We're asking, okay, what database I'm taking that information from. So I'm asking for RevGene, that's a database of annotations. This is just telling what region we are looking at. And now we're telling, okay, just give me the information of BRCA1. It's the only gene that I care. And then how you want the information. So I'm asking the output that I want is a bed file, which is this, which basically tells you the chromosome starting and ending position of something. Because we ask about, and at some point did I? Oh yeah, at some point we're going to ask what type of information we want, which is the coding exons. Yep.
Did we click send query to Galaxy?
Yeah, so when you're done everything, you can say at some point you get output, you're going to tell you coding exon and you send it to Galaxy, right? The button changes and says send it to Galaxy. And you're going to be sent to the Galaxy website, right? Oh, you need to follow me? Sorry.
yeah, can an entity reference as well.
Yep. So at some point it's going to ask you send the query to Galaxy and you click send it. Just keep it on the screen. That's going to be fine. Okay, yes, so the people who already reached Galaxy, you're going to see on the right side some spinning wheel. So so the Galaxy is trying to retrieve the data that you requested. Yep. So should I do it on the screen now?
Yeah, we are here.
Yeah, so coding exons.
Right?
Yep.
Coding exons.
And then you send it to Galaxy. Yep. So I'm going to do it now, right? So I'll show you basically what you see on the screen. So you see, Oop. So I went to the genome predictions. Do I need to change anything? No, right? Reference genes, genome. So you've done all this. You selected all the different things. Oh, BRCA1 already did it. So pretty much everybody reached that point, right? So we said the format is going to be a bed file, and we're going to send it to Galaxy, and then you click get the output. I mentioned to select only the coding exons because we only want the coding bases. And you send it to Galaxy. Yeah, we did it. I went too quick regarding Galaxy, but this is the Galaxy interface, right? On the right side, you're going to have some folder with your data. So here you can see our data being loaded to Galaxy, right? We need to wait until it gets loaded. And on the left side, you have all the tools available for you. All these are just tools that you can use for your analysis. You have a section for workflows. Those are the pipelines. I don't know where the tutorials are. I don't know if they are also part of the workflows, but I know there are tutorials available in Galaxy that you can follow for your analysis. Okay, so it's been loaded now and it's ready. So I said that we're going to be merging, right? So if I go, oh, well, let's visualize it first. So if I click here, see, I just click to my data, and now I can see the bed file, how it's being created. So that's the bed file of all my coding exons for BRCA1. So, but there's an issue with this. Can anybody point why you want to merge this file and what it means merging? You have an idea why I'm doing this? So the problem when we do this is we're getting all the coding exons for every isoform, right? So there's going to be exons that are duplicated or exons that overlap with each other. And I only said I want only the coding bases. I don't want to have multiple copies of the same exon or regions that overlap. I want a single track that is going to define all the the bases that are coding. So one thing that I could do is we're going to use, so I forgot how it was called. It's called operated. So let's do it differently. Let's go to, here we go. Operate on genomic intervals. And there is one that I should call merge. And already detect that I have some data here. And if it tells you what it does, there's an explanation. And this is what we want to do, right? So our data set contains coding exons that overlap with each other or they're duplicated. And I'm only interested about the coding bases. So if I do that, I can run the tool. Now you have a different set. So it's thinking, now it's working with it. And in a few seconds, I'm going to get what I want, which is a bed file with all the coding bases. So this is the type of things you can do connecting the UCSC genome browser with Galaxy. I mean, Galaxy is more than that, right? Galaxy, you can do, as I said, everything we do, by the way, everything we're going to do here in the workshop, you could do it in Galaxy. You may do it slower, maybe, depending on how many samples you have. But everything we're going to do in this workshop, more or less, except plotting in R, everything, all the analysis we're going to do here, you could do it in Galaxy. Except single cell, maybe. I don't know how the tools in single cell are here, but everything else, you could do it in Galaxy. So it just finished. So now we have a set of unique regions that define every coding base. Now, you can use this for variant calling. You can use it for different things.
So it is giving information about all the transcripts of this gene.
So originally, when we went to the genome table browser and we asked, give me all the coding exons, it gave us all the coding exons for every isoform in there, right? So, and what happened? And then we decided, I only want coding bases. I want a unique set. I don't want to have multiple. So if you compare this file with the original one, you're going to see that a lot of sections overlap or they're duplicated. And I want a unique set of coding bases. So that would be a way. We just did the merging operation, right? Which, sorry, I went really fast to this. Sorry, come on. It's giving you every base on that gene that has been annotated as coding. So this was our situation, the red one, right? So our original set, it was defining regions that overlap or were duplicated. And now what we get is the merge intervals, which is the bottom one. So the first we have red and now we have blue. That's the main idea. But it just was a test. So I wanted to show how these two data, so these tools that I think is going to be useful for you guys, you can connect them, right? We are not going to use these tools anymore, by the way. Sorry. It was just a demonstration of graphical user interfaces. I wanted to do something with a graphical user interface. From now on, it's going to be more manual work. Coding, right? So as I said, this is something that sooner or later, as a bioinformatician, you're going to have to learn. I'm not going to call it only coding. It's programming skills in general. It could be just command line, know how to use the command line interface. It could be actually coding code. But sooner or later, you're gonna have to, I think, right? So talking about coding. So I would say nowadays R and Python are the two most popular coding languages, scripting languages. So scripting meaning you don't have to compile the code to create a program. You just type your commands and you can run them. And there's an interpreter who's going to understand what you're typing and doing something with it. So R and Python are the most popular ones nowadays. So actually, I'm not trained with R. I'm not trained with Python either. I used to be trained with Perl, which nobody nowadays uses pretty much, right? Everybody has moved to Python or R. So even to me, it's hard nowadays to code myself or to talk about myself as somebody that programs because I'm using skills. I'm losing skills, I would say, right? I spent I don't know how many years, 12, 15 years programming in Perl, and nowadays it's like, okay, we move on with Python and R, sure. It doesn't matter what you learn, right? Maybe in 10 years from now, we quit using Python and we start using more modern languages. But anything you learn now, so a lot of these languages have commonalities, and you're going to learn structures, how to structure your program, and everything else. So you're not wasting your time if you learn a language now. Although it may change 10 years from now what we are actually coding in bioinformatics. I make also an effort to try to define how different they are from each other. Nowadays, there's a lot of overlap too. You generally say, oh, R is really good for plotting, right? Creating graphs and all that. It's true. It's maybe easier for that and maybe more difficult to learn. For plotting, maybe easier, so that's a good thing. But any library that you have here, it's moved to Python too. You have matplotlib. It's a library that allows you to plot really cool things, similar way that in Python does, although it's more, I think it's a bit more complicated. And the other way around is true. Some of the libraries that used to be only in Python are available in R, or you can connect them. You can incorporate Python code inside of the R code too. But yeah, the general idea is if you try to say, oh, I need to decide what are the two languages I'm going to learn, you need to think about what type of data you're going to be analyzing, if you want to do a specific plot or not. Nowadays, I would say single cell is there's a lot of application that we do with single cell, and I would say R probably is the most popular for that. So if you're working with single cell, then probably use to R. But again, tools that exist in one also exist in the other. There's a lot of overlap. No, you're not going to be wrong choosing one or the other. If you have to choose, of course. You can learn both or use both. There are other type of tools that are popular in bioinformatics nowadays. Have any of you heard about these things? Conda, Nextflow, or Docker? Well, some people, okay. So this is what we call package managers. You probably, if you work with Python, you use pip before. If you need to install a package, you pip, put the name of the package, and pip take care of anything you need to know about that package and installs all the dependencies and everything. So that's good. There's also the equivalent in R. Conda, what it does is a bit different in the sense that it's also a package manager. If you need to install a software, Conda is really cool because it doesn't matter if it's a Python package or R package or a command line tool or anything, Conda takes care of it. The problem when you install a software, if you're used to the graphical interfaces, is you download the full package and everything is there. Nowadays, there's a lot of people coding, and one software depends on another depends on another depends on a third one, and a fourth, and so on. And it's really hard to have, okay, I need to install this, but before I need to install that, because that needs that needs that. It gets complicated. So this type of tool helps you with that. I'll talk a little bit more about Conda in a bit later, but Conda does things a little bit different. Nextflow is becoming really popular. Again, probably everything we do here, you can do it using Nextflow pipelines. So Nextflow is a workflow manager. So if you go to the website, you're going to see there's a lot of pipelines there. So if you need to do variant calling, you can go to there, look for a variant calling pipeline, download it, and you have everything you need to run your analysis in a single package in theory, right? Nextflow can use Docker and Conda inside of Nextflow too, or it can be combined, all those things. Docker is a bit different, but related to the other ones too, in the sense that Nextflow is clearly for bioinformatics. Docker is used for everything. So let's imagine you need a specific software, but that software, again, needs dependencies that you need to install several other things to make it work. You can get a container, they call it. You can download a container with everything you need in that single container and run it. It doesn't matter if you're working a Mac computer, you can work in a different environment. It should supposed to have everything you need to run whatever you need. So you need to be a little bit aware of these things because it may save you a lot of time when you need to work in bioinformatics. Don't worry, it still doesn't work, so we're not going to do it again. But this is something that we wanted to think about it, right? So do you use ChatGPT? Yes? Can I see, how many people use it every day? Just to have an idea. Oh, wow, so everybody. Bioinformatics is not different. It is not. So you can use it pretty much every day, right? So how we use it, I was thinking, okay, how I use ChatGPT every day. So for writing code, you can use it for writing code. I'm not talking about tools specialized for something, or the language models, the different types of large language models, LLMs, that is being specialized to PubMed searches or reading papers for you and all that. No, I'm talking to ChatGPT generally, right? You can use ChatGPT for writing and debugging scripts. So if you have doubts about one piece of code, you can paste it in. ChatGPT will try to correct it and so on, right? It can even explain you the code, what it does. It does a pretty good job doing these things. It can annotate code. I think this is really useful sometimes. If I have code, I never annotate that code. I go there and say, please annotate it for me. And it's going to explain every line what it does, so I don't have to do it myself and type it. I don't know if you try this. I never tried this, but it probably can do it, right? You can probably giving, I obtained these results, what it means. I'm assuming ChatGPT is going to give you an answer. Always gives an answer, right? But that's a problem too, which is there's hallucinations. I remember when ChatGPT came out, I was trying to use it to get papers, right? I remember asking, okay, give me the top 10 papers in that field. Give me, because I want to just have an idea, and give me the PubMed ID of those top 10 papers. All the PubMed ID were wrong. Not a single one was correct. But ChatGPT was convinced, here you have the 10 papers, here's the PubMed ID. The titles were correct, as far as I remember, but the PubMed IDs all were wrong. Data privacy is another problem nowadays, right? I mean, Yale is now pushing a lot to have rules. We have different LLMs in Yale that are they have some privacy settings on them. There's one that's completely private. There's others that take your data, and they don't want us to use ChatGPT openly, right? I don't even know which one. Maybe Bonnie knows the ones we use. I don't even remember. Of course, there's no way to reproduce your data, right? If you use ChatGPT for an analysis, I don't know if you're going to do that, but it's going to be hard. In a month from now, it can be a completely different ChatGPT from the one that you used 4 weeks before. And they can have biases, of course, depending on how the data was trained. So you're already aware. I don't have to give you a class about this, you know. And of course, machine learning and all that would need a completely different workshop. Oh, and this, right? So you need to remember this. Always say thank you, because 10 years from now, who knows what's going to happen with the AI. So, but what tools are we going to use for this workshop? So our cluster, our high-performance cluster is going to be AWS. I don't know if you're aware of. So basically, Amazon, if I'm wrong, I don't know if it's true or not, that's what I remember long ago. I mean, I remember using also in a workshop like 15 years ago with AWS. It changed a lot completely from that time now. But I think Amazon, what would happen is Amazon sells stuff through the year. It needs some computational power for whatever sales it does. Christmas comes. All of a sudden, it needs 100 times more computational power to be able to sell everything they want to sell. They realized that through the year, 11 months, their computer power was idle. It was not used for anything. So they decide, okay, we can create a business out of it, which is why we don't sell the computational power to the people, and they can use it. So that's how AWS was born. That's as far as I understand how it was born. So yes, so that's going to be our HPC is going to be AWS. You don't care much because you're not going to see it that much, right? Your laptop and a browser is going to be the windows that are going to be used to connect to the AWS. Conda environments, that's what we use to install all software in AWS. We use a Conda. So we created Conda environments with all the programs we use to the workshop. That is not something that I recommend, and I'll tell you why, but you can do that. We're going to use the Jupyter Labs and notebooks, which is basically, if you use RStudio, it's similar to that, but I think it's cooler. That's what I think. Inside the Jupyter Labs, we have access to terminal, so we can use the terminal if we want to, but actually you can do everything through Jupyter notebooks if you want to. And some people mentioned about RStudio. You don't need to install it or do anything with RStudio. We're going to use the Jupyter notebooks. But if you want to and you want to use it, there's ways you can do that. So if you want to install RStudio and use RStudio on your laptop, there are times you can do that. So yeah, so these are the tools we're going to be using. And I want to mention something about Conda, right? The advantage of using Conda when you need to install something, you can, by the way, you can use Conda in Windows too, or your Macs or any kind of Unix. You can use Conda. Conda has an advantage, which is, first of all, allows you to create different environments, we call it. So let's say when you install a program in Windows, it's immediately available to you, and it's always available to you. When we work in bioinformatics, there's issues with that, which is programs change so fast that you need to update it every month. Let's imagine we work with CRAD, which is a tool for single-cell RNA-seq analysis. I do my analysis today. 3 months from now, there's going to be a new version. And I said, OK, let's install the new version. It's going to override the old one. And now all of a sudden, I need to reproduce the analysis that I did 3 months ago. I cannot do it because the version is different. Right? So Conda helps with this, for example. Right? So with the Conda creates what we call an environment. It was a space of programs that you install. You can activate it or deactivate it anytime you want. So let's say I install everything that I need for analysis today. I create that environment. 3 months from now, I want to update something. I'm not going to update it. I'm going to create a new environment with the new packages and create that new environment. If I need to go back, I'm going to say deactivate the new environment, activate the old one. And now I have all of a sudden the exact environment that I use for my analysis. The cool thing is I can say, oh, my friend wants to repeat exactly what I did with exactly the same programs that I use. So I can send him my environment. And he can reproduce the analysis created in that environment. So the way to encapsulate is really important for what we do, and I think Conda does a really good job. Before I said I install every single package for this workshop using a single environment, I don't recommend it because you have a lot of issues because there's incompatibilities with some programs that we use. So generally what you're going to do is if you work with single cell, you're going to have an environment for single cell. If you work for variant calling, you may have a different environment for variant calling. And within those, you may have different versions of the packages. So if you look at the one that I use at Yale, I have, for Serat, I think I have 4 to 5, depending on the version that I'm working with. And that happens. So you may end up having 10, 15 environments. But that's fine. I mean, not all of them are active. You only activate them when you need them. So, and one thing that I need to mention, so in Conda is that part here. This is important, right? I didn't use the word reproducibility, but we need to use it. So we are constantly being tested in science, right? Also in bioinformatics, to be able to express what exactly we did can reproduce our stuff. So Conda will help you with that. Somebody can ask you what versions you use. All of this. Here, Conda is going to give you all the versions that you use. Jupyter is similar in the sense it helps you a lot with science. Notebooks, what it does is combines and annotations in a single document. So you can start a document text, all of a sudden you create a plot. Let me create a plot. Documented the plot to run some code and run a code. So you can document a single document, and it's also helpful in the sense, okay, and how you do it. No, I don't have to. I give you. Just read it and you do it. So documenting and sharing, another important part in bioinformatics that we need to learn to do, right? Or, I mean, 10 years ago it was, I share my code, but it's not even annotated. It's going to be hard to read. So this type of tools helps you a lot. So Jupyter notebooks are really useful. RStudio has its own way to do notebooks. I like a little bit better in Jupyter. So that's why I think it's cooler. But RStudio also works. Originally, it was designed for Julia, Python, and R. That's where the Jupyter name comes from. Nowadays, I don't know, you can have a lot of different languages. I don't even know, but there's a lot of them. There's even ways to mix languages in a single document. Actually, we're going to mix, we could mix two languages in some of the documents, but there's ways to even mix R and Python code in a single document, and command lines too. And I think we're going to, it's 1, right? So it's a good time to stop and have lunch. Yeah? Okay, so we're going to stop here, and when we come back, we're going to start working with Jupyter Notebooks.